Okay, we want to look at an example of type of question I like to ask, and that is sketch the graph of a function whose domain is all real numbers, and such that the following criteria are met. And probably in the homework, if you've been doing the prerequisite homework, you've seen let's see, sketching a graph with these type of criteria, right, where the value of the function is, and then where it may be increasing or decreasing. But here now we're going to include limits, now that we've talked about limits. And so again, there's lots of ways this can be drawn. One thing for sure is you want to show, or you want to have a graph of a function, and so that means every vertical line will hit the graph at most one time. Also, I'm requiring the domain to be all real numbers, which means that every vertical line will hit the graph exactly once. Again, in the window I have, we want to make sure we bring the graph to the edge of the window so that we indicate that the domain is indeed all real numbers. Okay, so how do we start? And I'm going to do this again in pen, but I would encourage you to use a pencil as you're doing it, because you will often have to erase afterwards to adjust. And so let's start with these functional values. These are the easy part. F of -2 is equal to 2. So input -2, there's x equal -2, output +2. So I have the point -2, 2 on the graph. F of 0 is also 2, so input 0, output 2. And f of 2 is -3, input 2, output -3. Okay. Now, let's talk about the limits. What do we have there? Well, the first limit says the limit as x approaches -2 is 4. Okay, so as I approach -2, as x gets closer and closer to -2, the value of the function should be closer and closer to 4. Not to 2, but to 4. Where's 4? 4 is up here. So what's going to happen here? What do I have to have up here? What do I need to be approaching? Can I put a point up here? No, because the vertical line would hit the graph twice, and we would have 2 outputs for 1 input, and that's not a function. So I need to have an open circle here, and I do want to be approaching. I'm going to make just 2 little marks, real tiny marks there, because I don't know what's until I put in all the details what my graph will look like. But I'm going to be approaching 4, right? I'm getting closer and closer to 4. I don't know how I'm approaching. Well, it'll depend on some other factors, but I'm getting closer and closer here. Not to this point, but to this point. This hole again. The limit as x approaches 2, what? From the negative side is -1. Okay, so here's 2, and we're approaching what? It says from the negative side, so we're coming this way, and we're approaching what value? -1. Are we approaching -3 down here? This is the y value of -3. No, we're approaching a y value of -1. So again, what do I need up here? I need a hole, and I'm approaching it from both sides? No, just from the negative side. So from the left. So I'm going to put a little mark on this side. I need to be approaching that way. And then the last thing is the limit as x approaches 2 does not exist. Well, how can I draw a graph such that the limit does not exist at 2? Well, what I don't want to do is approach this hole from this side, because then the limit would exist. I would be approaching what? -1. So to keep it simple, since I have this point down here, why don't I make the limit from the right be approaching -3? I'll just make this little mark, approaching -3. And then I've got the limit from the right is -3, the limit from the left is -1. Since they both are not equal to each other, the limit as x approaches 2 does not exist. Now there are other ways I can draw a graph where the limit does not exist, but this is a simple way to do that. Okay, now we've got to fill in. We've got a lot more to fill in, right? I mean, what's going on in between each of these regions? Well, one thing we know, the f is increasing on these intervals, so from -infinity to -2, so everything less than -2. So basically I want to be going up, right, as we move from left to right for all values less than -2. And so where am I going to go? Am I going to go to this point? Am I going to approach this point? No, remember the limit had to be equal to 4 as x approaches -2. So in particular from the left, we've got to be approaching up there, and I've got that little mark to remind me of that. And so I'm just going to bring this up like something like that. And so it can be a line. You can draw it as a line if you want to keep it simple. I've got a little curve to that. Make sure you bring it to the edge here, right? Don't put a dot or a circle or anything here. If you want to put an arrow here to indicate it continues, that's fine. But it should go all the way to the edge. Don't stop right here. Bring it all the way to the edge, because the domain is what? All real numbers. Now what happens past here? Well, the only other thing that we have to make sure of is what? That it's increasing from -1 to 0. From -1 to 0. So that means for x equal -1 to 0, I've got to be moving up. Okay? All right. Now, assuming I want to keep it simple and approach that point right there, I can do that. I can move up like this. Where do I need to come from here then? I need to come down far enough so that I can then move back up, right? So I'll just bring this down here, kind of steep, and then right there when it becomes -1, I've got to make sure that what I'm increasing. So I'm going to begin to, I'm going to turn that around, and I'm going to bring it up towards 2. In fact, I can go right to 2, right? Keep it simple. Right? Now, what's left to draw? There's no other requirements. So as far as increasing or decreasing, so remember I need to approach this hole from the left. So I'm just going to bring this down and approach that hole from the left. And I need to approach this point from the right, we said. And so I don't know, I'll just draw whatever. Bring it all the way to the edge, though. Real important to bring it all the way to the edge. So here's a possible graph that satisfies these requirements. And all I'm going to do to check your graph is, first of all, make sure it passes the vertical line test. Every vertical line hits the graph only once. Look at here. We pass through that hole, and then we hit the point. So that's still good. Here we pass through the hole and hit that point, just one point for every vertical line. So it's a function. And every vertical line hits the graph exactly once. So the domain is all real numbers. F of -2 equals 2. Yeah, there's the point. It's not equal to 4, it's equal to 2. F of 0 is 2. F of 2 is -3, right? Not -1, because there's the point. The limit, though, as x approaches -2. But where's the graph going as we get close to -2? It's going to there. It's going to 4. Right? So that's good. The limit as we approach 2 from the negative side, is that going to -1? Yeah, it's going to right to this, the coordinates of this hole. Going to -1. The limit as x approaches 2 does not exist because the limit from the left is -1, but the limit from the right is -3. And therefore the limit as x approaches 2 does not exist. And again, we're increasing, going up from, for all values less than -2, we're going up, and then for values between -1 and 1. Right? And there it is. There's a possible graph of the function. There are other possibilities, but that's one possible graph. So, when we're talking about limits that do not exist, right? Here's a good way to, this is sometimes called a break in the graph, so to speak, where we have the limit from the right is one value, limit from the left is another value. That's a nice way to draw a situation where a limit does not exist. But there's other ways that limits do not exist. And I want to illustrate a very interesting one here in closing. I'll look at this function, sine of 1 over x. Now we looked at sine x divided by x as x approaches 0. I want to talk about the limit as x approaches 0 of just sine of the quantity 1 over x, right? This is sine of 1 over x. Okay? And I want to look at this graphically. Clearly it's undefined when x is 0 because I can't divide 1 by 0 and get a real number. But I'm going to look at this graph close to 0. And I'm going to look with a y value of -2 to 2. Let's first input this function. Make sure, of course, mode-wise we're in radian mode, which I am. And I'm going to do sine of 1 divided by x. Right. And I'm going to open my window. X is going to be -3 to 3. And y is going to be -2. Oops. Y is going to be -2 to 2. Okay. All right, so here's the graph, and you can see, notice for large values of x, like as x goes to infinity, 1 over x is getting smaller and smaller, getting closer and closer to 0. Sine of 0 is 0, so we're getting closer to the x-axis. Same thing as x goes to minus infinity. But as we get close to 0, then we see some ups and downs, right, bouncing back and forth. And you know, up here is, you know, positive 1, down here is negative 1. That kind of makes sense. We know the sine function bounces between 1 and negative 1. So it looks like it goes up, down, and then up, down. You know, what's the limits? Are we approaching 0 as x gets close to 0? What's happening there? Well, let's sort of zoom in a little bit here. I think I say let's zoom in between negative 1 and 1 next. So let me change my window to negative 1 to 1. And let's take a look at, you know, squeeze in a little bit. All right, so there's the graph. It goes up. Oh, it does a little bit more than I thought. It looked like it just went up, down, and then back up. But so let's zoom in a little bit more. Let's go to negative 0.1 to 0.1. So let's zoom in by a factor of 10. There it is. Ooh, look at that. That's doing a lot more than we thought maybe. Let's zoom in a little closer and let's see if we can see what we're approaching. As x approaches 0, right? We're real close to 0. Let's go to this window from negative 1/100th to 100. So that's pretty close to 0 here. Let's see if we can see what we're approaching. Okay. So let me tell you this right now at this point. What your graph, what is showing you right now, is not the graph of this function. Your calculator cannot handle this function. Okay? This is incorrect. This is not the graph of this function. What is happening? Okay, I'm going to explain first of all in words, and then I'll look at it analytically. Basically, what's happening is as x gets closer and closer to 0, 1 over x is getting larger and larger. Okay, you take 1 divided by a smaller and smaller number, the output gets bigger and bigger and bigger. And the sine function, as x, the input gets bigger and bigger, it just keeps bouncing between 1 and negative 1. In fact, this goes on forever, and so we have an infinite number of times where this function is equal to 1 and an infinite number of times where it's equal to negative 1 as we approach, you know, from any value of x here greater than 0 to 0, there'll be an infinite number of locations. This function begins to oscillate so rapidly back and forth, it cannot settle down to any particular value, and we'll see that the limit does not exist. The problem with the graph, the oscillations are so rapidly going back and forth, the calculator can't keep up. It samples a point here, but then the next point it samples here is on a whole different curve. It's kind of like as we're approaching 0 here, the graph just has all these wild oscillations back and forth. You know, it's hard to even to graph, and the calculator can't handle it. So it plots this point here, and then maybe it plots this point here, and then maybe it plots this point here. So the graph looks something like this. That's why it's kind of choppy too in certain areas. So the graph looks like that instead of what it actually is supposed to look like. Okay, so what is happening analytically? Let's see. Well, first of all, remember sine of t is equal to 1. If t is what? Pi over 2. Think about the unit circle to help you out with that, right? We're at the top of the unit circle there. The y coordinate is the sine, value of sine of the angle. If we're pi over 2 or 90 degrees, if you remember, pi over 2, then sine is 1. But then I can go all the way around by a multiple of 2 pi, right, all the way back up, and we'll be back to the same value of 1. Remember, sine has a period of 2 pi. So pi over 2 plus any multiple, n is any integer, any multiple of pi. And if I write this as over a common denominator of 2 and just clean this up, I get this expression here, right? So 2n pi is equal to 4n pi divided by 2. And then I can factor out this common pi and add these two together, and I get pi times 1 plus 4n. So this is true for n equal any integer, 0 plus or minus 1 plus or minus 2, and so on. Similarly, sine of t is equal to negative 1 if t is 3 pi over 2 plus any multiple of 2 pi. which I simplify down to this expression for any integer n. Okay. And again, this is an infinite number of values here. N is equal to 0, 1, plus or minus 1. There's an infinite number of values of n, infinite number of values where sine of t is equal to 1. Now, look at our function. Sine of 1 over x, therefore, is equal to 1 when its input 1 over x is equal to this thing here, right? And if 1 over x is equal to this, then do the reciprocal of both sides. X is equal to the reciprocal, right? 2 over this, right? Again, for all integers, infinite number of values. In particular, it's true for all the whole numbers, positive 0 and positive integers, 0, 1, 2, 3, and so on. So when n is 0, what do we get here? We get 2 over pi, right? 2 over pi. When n is 1, I get 1 plus 4, 5, 2 over 5 pi. When n is 2, I get 1 plus 8, 2 over 9 pi. When n is 3, I get 2 over 13 pi, and so on, right? How long can that continue? Forever, right? There's an infinite number of values here, all right? However, look at these values. What's happening to them? 2 over pi, 2 over 5 pi, 2 over 9 pi, and so on. What are these values doing? Getting bigger or smaller? They're clearly getting smaller. They're getting closer and closer to 0, right? Dividing 2 by a bigger and bigger quantity, it's getting closer and closer to 0. And so notice this is 2 over pi. Pi is about 3.14. This is a little bit less than 2/3, a little less than 2/3. But what this is saying is that there's an infinite number of values of x from, right, because there's an infinite list here, from 2/3 to 0, where the function is equal to 1, right? Infinite number of times. In a similar way, we can show that the function sine of 1 over x is equal to -1 for an infinite number of ways. And you can look through this analysis. It's very similar to what we have above there. I generate this list of values, this time from 2 over 3 pi, which is 2/9, or about 0.22 something. There's an infinite number of values from this value to 0 where the function is equal to -1. And so as I said before, this function, as it gets close to 0, it just begins to wildly oscillate between -1 and 1. It never settles down. You don't get close to any one value. You know, if you're trying to do a table of values, you just never get anywhere. You just keep bouncing back and forth. And the limit does not exist. And so this is a different way where we see a limit not existing, as opposed to where the limit exists from the left and from the right, and it's just not equal, versus this situation. Okay, so there are some strange and different ways that we can have limits not exist. We can define functions in interesting ways, but I just wanted to show you that as a sort of a side note in a way, but a good illustration. Okay, so what we're going to move on now in the next set of lectures is we're going to begin to look at limits algebraically or analytically. So in these videos we've been talking about numerically and graphically, which is a way to estimate values of limits, but now we want to actually find out, how do we find out the exact value? How do we do it algebraically or analytically? And we'll look at the basic limit laws. We'll talk a little bit about something called continuity, and then we will begin to look at that process.